College Algebra, Lesson 4.5, Solving Exponential and Logarithmic Functions, page 398. All right. A couple of the things that we found as far as exponential equations is that we've been looking at logarithms, and we're going to continue doing that, but we're also going to be looking at exponential equations as well. And so what this means is what we're looking for is we're looking for our exponent. So, given the information that we have, we're looking to find out what x is, so that 3 to that x power is going to be 20. Well, we know that 3 times 3 is 9, so 3 squared equals 9. We know that 3 cubed equals 27, so we know to get 20, our x is going to be a number somewhere between 2 and 3. But what number is that? And that's where logarithms come in as far as helping us to be able to determine what that x is. Alright, so when we have a base and we're comparing it to another base, so for example, if we had 2 to the 5x power and we said that was equal to 2 to the 6th power, since our bases are the same, then our exponents are also going to be the same. Which means we can completely ignore our base and we can just say, well, our bases are the same, so our exponents must be the same. So that means my x value has to be 6 over 5. So 2 to the 5 times 6 over 5 equals 2 to the 6th power. And when we do some canceling here and here, we get 2 to the 6th equals 2 to the 6th. So, all that to say is that if our bases are the same, our exponents also must be the same. And if you remember, when we were talking about exponents, those are logarithms. So that gives us some direction to go as far as logarithms are concerned. So, a to the x equals a to the y, and these two arrows here basically represent the word when x equals y. That's the base exponent property, top of page 399. So when we have 2 to the 3x minus 7, and I say that equals 32, my exponent on my 32 is a 1. Well, I can't say that equals that because my bases are not the same. So if I can somehow make my bases the same, then I can say that my exponents are the same. So I can write, instead of 32, I can write this as 2 to the 5th power. So now that my bases are the same, I can say 3x minus 7 equals 5, 3x equals 12, x equals 4. So I can go ahead and solve that because I was able to change my 32 to 2 to the 5th power. Which brings me to another property, and this one's called the property of logarithmic inequality, and you will use this a lot. This says log a of m equals log a of n when m equals n. Okay, very important. What that's saying is that if we have m equals n and we take the logarithm of both sides, we can say that those are equal as well. And our logarithm, our base, can be anything we want. I mean, normally you're just going to want to pick 10. Okay? So what that means is, if we have 3 to the x power equals 20, we can say that my 3 to the x power is m, the 20 is n, so that means I can say that these two are equal. So I could say the log of 3x equals the log of 20. Okay? Then I can do my handy dandy math that we've been doing for a while there and be able to, let's get this out of the way, and be able to use what we've already done, and we can take our x right here and move it in front. So x log 3 equals log of 20. Divide both sides by the log of 3. You just do your typical algebra. Cross those out. So my log equals, or my x equals a log of 20 over the log of 3. Okay? So if you take your calculator out, you can take the log of 20 and get some number. Take the log of 3 and get some number and actually divide it out, and you will get a number such as 2.7268. A number similar to, or close to, approximate 2.7268. Okay. Now, for those that are really thinking, there is another way to solve this. Just a minute ago, we took the log of both sides, and the log that we used was base 10. But what happens if we take log base 3 of 3 to the x equals log base 3 of 20? Remember, a couple lessons ago, we found out that when this base and this are the same number, those actually equal 1 and can disappear. And that leaves us with x equals log 3 of 20. But your calculator won't do log 3 of 20, so you have to use that change of base formula, and you end up getting, again, log of 20 over log of 3, which is going to give us the same answer, 2.7268. Okay? So there's two ways of doing that. So let's look at example 3, top of page 401. 4 to the x plus 3 power, and we're saying that equals 3 to the negative x power. Okay. So let's take the log of both sides. Log of 4 to the x plus 3. So we made it log with a base 10. Okay, now we take our exponents and move it to the front. We're going to put that in parentheses so it doesn't look like x plus 3 times log of 4. The x plus 3 is all being taken times the log of 4. And that's going to equal negative x log of 3. Okay? Now we're going to distribute this x plus 3. And when we distribute that, well, actually we're distributing this to each of those. So we get x log of 4 plus 3 log of 4 equals negative x log of 3. Okay, now we need to get the x's all on the same side. So we're just doing, again, algebra. We're finding out what our x is. So we're going to move this here, this whole thing over here, and we're going to move this one over here. So let's just switch those around a little bit. We'll do that in yellow. X log of 3 plus x log of 4 equals negative 3 log of 4. I'm going to look here, factor out an x, next step is I'm going to divide both sides. And I'm going to divide both sides by this here. So then I get x equals negative 3 log of 4 over log 3 plus log 4. Now what I can do is I can take my calculator, find the log of 4, and I can use that answer here, multiply it by negative 3, and I can also use that number here and add it to whatever the log of 3 is. Since we're in base 10, you can use your calculator for all of this, and you'll get negative 1.6737 as an approximate value. So when you have a variable that's in an exponent position, you're going to want to use logarithms in order to solve it. Alright, so let's look at a natural logarithm. Let's look at e, and we're going to go 0.08 t, and we're going to say that equals 2500. Okay, so what we're going to do here, since we have a natural logarithm, is instead of taking the logarithm, the log, we're going to take the ln of both sides. Okay, so when we take the ln of both sides, if you remember, this will go away, because that is the same thing as log base e of e. And remember, when those are the same, it becomes a 1. So my ln of e always is a 1, so that's why I prefer to take the ln rather than a common logarithm. So that gives me 0.08 t equals ln of 2500. Solve for t by dividing by 0.08. Those cancel, and I get t equals ln of 2500. Use your calculator, divide by 0.08, and you get 97.8 for an answer.